All right, let's get started. So you had a guest lecture yesterday, or on Friday, I'm sure that, or Monday. Today's Wednesday. Monday. I'm sure that was all very fun and dandy. If you want, since that is not online, if you want to go on to YouTube, you can always get to my channel just by searching my name. This is me in the funny hat. This is a guy from Australia. Very nice. We're Facebook friends. Same name. This is me. You'll notice there is like almost no videos here. There's some very old stuff. If you go to playlists, however, you will see several public playlists, each of which have a zillion videos. So things like the fall 2017, that's only got 3 videos because that's all we filmed. But if you look at the spring ECE 2017, that's all of them. I don't recommend watching them all in one go, though. You can go scroll through this, and it tells you what everything is, and it's got names on things. There are no dates on this, so this year I'm dating every video. But anyway, so you can get to this. Ignore the 263 stuff until you get to 263. So last year's ECE 260 stuff is available for secondary viewings. That's that. So you should be able to find it. Just again, my name. It's on the syllabus if you can't find it. Let's go over to Open Board. All right, so I have it on good authority that you made it through what? What was the last thing you had in your notes? Let's see if they match up. ASCII code, ASCII. And ASCII stands for what?
American Standard Code for Information Interchange.
The American Symbolic Code for Information Interchange. Okay. Yes, ASCII. How many bits wide is it? 8 bits. Or 7 bits, depending on who you ask. There's extended ASCII that's 8 bits. Regular old ASCII is 7 bits. And it represents all the letters, uppercase, lowercase, the numbers, punctuation symbols, some control characters. But we did not make it to BCD, right? No BCD? We did make it to BCD. Then gray code. Gray code. Okay, gray code is fine. All right, up till now, everything that we've done in terms of number systems has been positional, right? Every place, every digit place, allows you to directly translate it into a number. Well, gray code is a little different. Gray code is a lot more about physical transitions than it is about representing a particular number. And I'll give you an example. Let's say I have a couple of strips of paper. All right, and on this strip of paper, I have 2 sensors. One sensor is, let's try that again. One sensor is right here. The other sensor is right here. And the paper is going to move under these 2 sensors. So it's got 2 tracks. And the sensor is either going to tell me, do I have a light colored space or a dark colored space? You can think of this as what kind of happens on a Scantron. So as I go along, I have 4 areas. All right, let's go with this. And I'm going to leave the first 2 white. Then I'll have, if I can do this correctly, 1 white and 1 dark. 1 dark and 1 white, and then both dark. Now, I think at this point we can see that maybe if we looked at this as binary, maybe we could see that this was a 0, this was a 1, this was a 2, and this was a 3. It's binary, so a no color is a 0 bit, filled in is a 1 bit. So as this sensor goes along, it's going to detect 0, 0, 0, 1, 1, 0, 1, 1. Nothing too crazy there. It's just a piece of paper. Let's add a piece of tape to this. I'm going to tape this piece, this side of this paper over here. So now we have a cylinder of paper. Again, going 0, 0, 0, 1 along the back here. it'll be 1, 0, 1, 1 cylinder. So it's going through the sensor. So I should see 0, 1, 2, 3, 0, 1, 2, 3 over and over and over again. Now, everybody okay with what I've done? All right, I've just got this piece of paper. This should work fine. I've got two sensors. They're going to count. Imagine now this is no longer a cylinder, but it's now a tire. And that along your tread, you've got those setups. So you've got a tire now. I should be able to tell what position my tire is in. It's either in position 1 or 2 or 3. Right? Think of this as almost how an odometer works, right? It has to track how many times around your wheel goes. So this is where we're using this gray code as a positional encoder. Well, here's the thing, though. We've got these two sensors. And as long as those sensors are manufactured with exacting 100% tolerances, everything is going to work out just great. But imagine for a moment, let's exaggerate this. Here's one sensor. The second sensor should be on this line, but let's say that it's over here a little bit. Now what happens? Well, thank God for movie magic here. Here I've got it. And it's starting to go across. And right here, we're seeing a 0, 0. And everything is fine. We see a 0, 0. Right up here, we see a 0. Now, the next number we should see after 0, 0 is 0, 1. Because we're counting. 0, 0, 0, 1. What happens here? We see, well, actually, this 1 connects before the first sensor. You see how it's already on the bottom side is on the dark, whereas the light side has not transitioned yet? So is that okay? Do we see a 1, 0, 0, 1, 1, 1? We see a 0, and we see a 1. So everything is fine, even though these have been manufactured terribly. Okay, now we're in 0, 1. What should we see next? We should see a 1, 0. Here's where things become interesting, because here I see a 0, 1, and now I see a 0, 0. The upper one is still on this track here where there's a 0, and the second one is on the next track, which is also a 0. So what does it mean? Imagine we have our perfect tolerance set up here. What does it mean if we go from a 0, 1 to a 0, 0? What does that mean in terms of this wheel that's turning? It's going this way, right? We went from 0, 0 to 0, 1. So it's going backwards, which is cool. We can tell the position of our wheel and the direction of our wheel. But obviously, that's not what's happening in this case. We're traveling to the right, and we see a 0, 0. So suddenly, if we have some sensors on this, a little bit of brains, we suddenly think we've gone from here back this way. And then we move a little bit farther. Now we move here. Now we've moved into we're in 1, 0. So what does that mean for our brain? Our brain thought that we were here, then we were here, and then we jumped here without touching this at all, which can't happen. So we've established that there is a problem with counting in binary in situations like this. Enter gray code. Same setup. We've got let's do it in a color that makes sense. We've got our 4 positions. Goes across. We've got our 2 tracks. But now I'm going to divide it up a little differently. Still 4 pieces. This is 2 bits, so we have a total of 4 positions. Now I'm going to go 0, 0, 0, 1. So it's starting off the same. 1, 1. 1, 0. 0, 0, 0, 1, 1, 1, 1, 0. Same problem. We have a poorly manufactured setup. It should be perfectly aligned, but it's not. Now what happens as we go along? Well, here we see, again, we are straddling the line between 0 and the previous number. So once we're in 0, we're fully in 0. Everything looks good. We detect a 0. Here, same situation. We don't have a problem because we're going into a filled-in area. So even though we're straddling the line, previous we saw a 0, so we still see a 0. And now we've switched into 0, 1. So this transition works out okay. Next transition, though. This is where we had a problem before. But now notice we're going on the bottom from a filled-in area to a filled-in area. So no problem. We're still in 0, 1. Now, when we finally cross the border, now we're fully into 1, 1. So there was no glitch here. As we continue on, we're in 1, 1. Now, here the bottom is changing first. So when we do this, what happens? Right there, we've changed from a 1, 1 to a 1, 0, which is what we're supposed to be transitioning to anyway. So every one of these transitions is okay. Now, the reason this all works out and why gray code is so great is because only one bit position can change between sequence values. So from 0, 0 to 0, 1, only one change has occurred. From 0, 1 to 1, 1, only one change has occurred from 0 to 1. From 1, 1 to 1, 0, only one change has occurred. If you're watching this later, I'm intentionally skipping a certain thing. You'll see why in a second. Let's go back to binary for a moment. All right, this isn't gray code yet. This is just binary. How many values change from 0, 0 to 0, 1? Just one. How many change from 0, 1 to 1, 0? Both of them change, and that's why there's a problem. Anytime more than one digit changes, if you don't have perfect alignment, you're in trouble. From 1, 0 to 1, 1, how many digits change? Just one. Now, remember I said that this looped around on itself. So from 1, 1, we actually go back to 0, 0. So how many digits change from 1, 1 to 0, 0? 2. Both of them change. So let's check now back at gray code. Do we still hold on to that? If we add on the next digit, that's back to 0, 0. How many change from 1, 0 to 0, 0?
1, 1.
Only one. So this sequence, because it is a sequence, it's not a number system per se, it's a sequence, allows us to provide only one digit change. Now this doesn't just work for 2 bits, it works for 3 bits and 4 bits and 5 bits. 2 bits is easy enough to understand. You should memorize this sequence because come chapter 3, it's going to become really important. 0, 0, 0, 1, 1, 1, 1, 0. How many people have made flashcards for the first 15 digits of hexadecimal? A few people. Well, let's make it easy. Why don't I give 2 bonus points on the first exam if you make flashcards for hex, octal, and binary for the first 15 digits? 2 bonus points on first exam if you make flashcards for binary, octal, decimal, hex by, I don't know, Friday? By Friday. First 15 digits. They can be digital flashcards, postcard flashcards. I personally use a flashcard app called Anki. This thing, an Ankh. I believe it's Anki. It is kind of cute in that it will ask you, it'll show you the flashcard, and you say the response in your head, and then you say, show me the answer. And then you just tell the flashcard app, did you get it right or get it wrong? And if you got it wrong, it'll ask you again in like 2 minutes. If you got it right, it'll ask you again in like half an hour. So you just spend like 10 minutes a day on this thing, going through this. It's some sort of learning thing where you reinforce the stuff that you don't know, and the stuff that you do know, you go longer and longer between asking. Helps you remember stuff. So first 15, it has a computer version too, Anki, flashcard app. So that's 2 bonus points. I digress. So for longer digits, it gets harder. For 3, I can almost do it. So 0, 0, 0, 1, 1, 1, 1, 0, and then back to 0, 0. There's your 2-digit sequence. For a 3-digit sequence, maybe I can do it by memory. 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1. Then I got to really think about it. I'm trying to make sure that I end up at 0, 0, 1, or rather a different number because I've already got that number down. It becomes kind of complicated at this point, even at 3 digits. What haven't I done? 1, 0, 1, and then 1, 2, 3, 4, 5, 6, 7. Oh, I did it. 1, 0, 0. I did it, I think, because then that loops around. It's not necessarily the only gray code sequence that exists, but if I ask you to do 4 digits, it gets exponentially more complicated. You can kind of notice a bit of a pattern here. Just like binary, it's still groups of 2 and 4, and so on and so forth. There is definitely something to do with the power of 2 here. I'm going to codify this into a very simple way to go from a binary number to the corresponding sequence of gray code. So if I want, say what did I do as an example? 16 plus 6, 22nd. If I want the 22nd sequence in a 5-bit gray code number, first thing I do is I've got to write out the binary version of that number. So there's 16 plus 4 is 20, plus 2 is 22, so that's 22. This is in binary. Now I want to know what is the 22nd sequence in gray code, the 22nd number in the gray code sequence. Well, here's how it goes. Step 1, bring down, what does MSB stand for? I think I've used it a few times. Most significant bit, the leftmost. Bring it straight down. 1. Then, step 2, digit plus next digit. What is 1 plus a 0? 1. So 1 plus 0 is a 1. And repeat. So then you take 0 plus 1. What is 0 plus 1? 1. Next digit. What is 1 plus 1? It is 1, 0, or it's 2, depending on which base you're looking at. In this case, we're going to look at binary. And we only keep the least significant digit. So let's say 2a. Keep only least significant bit of sum. So 1 plus 1 is a 0. Finally, 1 plus 0 is 1. So that is the 22nd number in the 5-bit gray code sequence. So what I'd like you to do right now is find me the 21st gray code number using 5 bits. Come on in. You're on camera too, so.
Which pivots did you use for
D0 through D7. If you're having trouble dealing with the 21st number, 21, start looking at your digits in powers, 1, 2, 4, 8, 16, 32. I know that there are no 32s in 21 because 21 is less than 32. I know that there must be at least a 16, so 21 minus 16 is math. Hold on. 4 plus 1 is 5. So there's no 8s in 5. There's a single 4 in 5. There's no 2s in 1. There's a 1 in 1. So that, my 5-bit number. How many people were able to get that far? If you cannot, you need to do more problems converting. Just pick random numbers out of a hat and turn them into binary. Okay, so then the sequence is pretty clear. You write down the number. First digit comes straight down, and then you add across. So 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 1 is 1. So the 21st gray code number, the 21st gray code number is this value, which happens to be all ones in binary, but it's how you look at it. So this is the binary number 21. This is the 21st gray code sequence. They're both 5 bits of binary, but it's all in how you look at it. And if we can go from binary to gray code, we can go from gray code to binary. So if we have a gray code value, doesn't matter what it is, this is in gray code, we want to know the binary sequence number. Here's how we do it. Step 1 is the same. Bring that first digit down. Step 2, take the binary bit, add it to the next gray bit. 1 plus 1, oh, and we'll put the same addendum here, 2a, keep LSB only. So what is 1 plus 1? Keeping only the lowest bit. 0. 1 plus 1 is a 1, 0, so you keep the lowest bit, 0. And repeat. So now 0 plus 0 is, don't all jump at once. It's 0. 0 plus 1 is 1. 1 plus 1 is 0. So this, what is this in decimal? This binary number. 16 plus 2. Again, 1's place, 2's place, 4's place, 8's place, 16's place. So 16 plus 2 is 18, yes. So this gray code number is the 18th in a 5-bit sequence. How many total values are there in a 5-bit gray code sequence? How do we even figure that out? Raise your hand, don't shout it out. 2 to the 5th. We got 5 bits. Each thing can be 2 values. So that's 2 to the 5th. And what is 2 to the 5th? One point. Powers of 2 up to n equals 39. And by that, I do not mean exact values. I mean memorize n between 0 and 10. That's 10. And then memorize the fact that 10, 20, and 30 are kilo, mega, giga. So when I ask you what is 2 to the 15, I do not want an exact answer. I want 32K. That's close enough for everyone here. Okay? I'm sure that there's an exact number. Someone could punch it into their calculator, get an exact number. That's fine. But it's enough to know that we're talking about 32K. How did I get 32? Well, 2 to the 5 is 32. 2 to the 10 is 1024. It's 1,000. If I had said 2 to the 25, that would be 32 million or 32 mega. So, today we just earned 3 bonus points just for making flashcards. By Friday. You got to bring them in, show them to me. I'll check you off on a list, and that'll be that. So that's gray code. You did not start talking about logic. Is that correct? No Boolean logic. These are things that are unfamiliar to you. All right. Well, we're kind of moving tail end of chapter 1 into chapter 2. There are 3 functions that make the world go round. They are in charge of the banking sector. They are in charge of your smartphone. They are in charge of keeping time. The 3 functions that rule the whole world are and, or, and not. That's it. Those 3 functions together make everything else possible. And because they are 3 functions that are so powerful, we have a lot of ways of talking about them. First, we've got their names. Okay. We've got some symbols. And we actually have lots of symbols. Depending on what field you go into, the symbols are different. If you're in math, those are your symbols for and or. And this is probably for not. If you're in computer science or digital logic, and, or, not. If you're in my class, we're going to be using the dot for and, plus for or, and we're going to be using something called the over bar. Notice that there's space for a character here. The bar goes over whatever you're inverting. So it's called an over bar. So we've got and, or, not. And also, depending on where you are, you'll use these other symbols. That covers math symbols. Graphical symbols also exist. The and symbol is represented by a sort of elongated D with inputs on the left, outputs on the right. An or function is a Star Trek communicator turned on its side. Again, outputs on the right, inputs on the left. And a not is a triangle with a bubble. Inputs on the left, outputs on the right. And in fact, the bubble itself means more than the triangle. The bubble is really the thing that tells you that this is a not gate. And I should say that explicitly. These are called gates. All right. But what do they do? I guess, is the first question with these? Well, we have a way of representing what they do, something called a truth table. A truth table defines all truth for a function. It tells you everything you ever wanted to know, and nothing more and nothing less. If you have an AND gate, or an AND function that has two inputs, x and y, and you want to know what the output is, the output of the AND gate, you create a table. And you go through every possible combination of x and y. The easiest way to do this is to count up in binary in however many input bits you have. So I have two input bits, so I'm going to count 0, 0, 0, 1, 1, 0, 1, 1. Small side note, if you are ever talking to a math person, you will know it because they will put their truth table like this. 1, 1, 1, 0, 0, 1, 0, 0. For some, oh, my face is in the way. Let's do this. Haha. Math people can only count backwards for some reason. So when you take probability or statistics or something where they start talking about logic, you will see them do this. And hopefully I will have ingrained in you the correct way to draw truth tables. And you will get very annoyed with these math people. But understand that it's the same pieces of information. Because if this is your math professor's truth table, this is AND. Here's how an AND works. An AND is true only if both of its inputs are set high. So unless they're both high, the output is a 0. Now, math people will do the same thing. They'll just put it on its head. Okay? It's the same table, just in a different order. But for the rest of time, we will strike this from all memory. We don't need to deal with that. That's AND. It's the proverbial usage of the word AND. You must do this and this in order to get something. Okay? My mother explained AND to me at a very young age. I had to do this and eat my dinner and do that before I could go and climb a tree or whatever it was I was doing that day. Or is a little different. Or is one or the other or both. So again, the left side of the truth table is exactly the same. 0, 0, 0, 1, 1, 0, 1, 1. But or, if either x or y are 1, they go high. If both of them are true, we still go high. Now, these two functions can be expanded to more inputs, and we'll talk about that. Not is special in that it's a unary operator. It only takes one input, x. So there's only going to be a certain number of rows in my truth table. If I have one bit of input, I have 2 to the 1 rows. 2 to the 1 is 2, 0, 1. And not is the exact opposite. Put in a 0, you get out a 1. Put in a 1, you get out a 0. When we are building circuits like this, we will probably somewhere have a truth table available to us as we're building our circuits. But when we test it, we typically don't test it and just see a truth table. We have one more way of visualizing this. New page, come on. Called timing diagrams. Timing diagrams are usually generated by a logic analyzer. They show values over time. So I might have on the y-axis a spot for x, a spot for y, and a spot for f, the output of my function. Each of these is itself its own little graph, and time goes this way. So I might see, and so what I have is effectively 2 different states, or 2 different levels that these can be at. To keep myself neat, I'm going to draw in some yellow lines very lightly. Okay, you don't have to draw those. These aren't part of the table, but I want to show you what is going on inside of a timing diagram. So I'm going to give myself some guidelines here. And then I'm going to draw in what we might see on a logic analyzer. So first thing, we're going to be generating our inputs, because they're inputs. We have to generate them. So we'll use binary is fine. So we'll have a 0 and a 0. That's our first input here. Our second input will be a 0, 1, a 1, 0, and finally a 1, 1. So now I can go back and finish this up. When I go from a 0, 0 to a 0, 1, you'll see a vertical line there. Let me do it in bold too. So 0, 0, 0, 1, 1, 0, and finally 1, 1. That's what I will have to generate as part of my testing procedure. And part of the lab today is setting up the protocol generator to do this. Then we're going to see the output, and you're going to have to interpret the output. If, for example, I gave you this, or you saw this on the logic analyzer, and again, this is one complete cycle. It goes 0, 1, 2, 3, and it's going to repeat. It's going to keep on going. 0, 1, 2, 3, 0, 1, 2, 3, over and over again. Based on the notes I just gave you, this describes an elementary function, one of those functions that makes the world go round. What function is it? Called on you several times today. Somebody else. I've called on you too. Somebody else. Yes. It's an AND function. You can tell that, especially if I add in a little annotation here. Let's write in some values. 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1. If I were to take this, and I'm not sure that I have, maybe I do. Let's try it. We're going to try a new thing. It may blow up spectacularly in my face, but we're going to try it. Group that, copy that, new page it, paste it. Aha! That was fun. If I put it this way, aside from the fact that F is on the left, I've got my truth table. Here's my output. Here's my input. It's the truth table. Can I mirror it? Oh, that would be just whiz bang. Can I? How do I? Can I right click on it? No. Okay, I can't mirror it. That would have been really cool. But that's it. Truth table and timing diagrams are very closely related. All right. So that's where we're headed. You're going to be constantly looking at, whoa, oh dear, oh dear. You're going to be constantly looking at timing diagrams. I can't rotate you now. Oh, there it is. Looking at timing diagrams to find out what they mean. Now, it would be nice if we could just use one of these gates and solve all the world's ills, but usually we have to use more than one gate. So we have math for this. Okay, and this is going to lead into Boolean algebra, which is just like regular algebra, but instead of having to do a lot of math, you really only have to know ones and zeros. So an example of a function could be mathematically defined. F equals X or Y bar Z. Perfectly legitimate way to represent a function. This uses all three. One of the things that you'll notice is oftentimes and will not use a dot. It will just use the fact that they are next to each other. So it will be implicit and, just because they're next to each other. This has three variables, x, y, and z. One of them uses the not function, y not. Z is anded with y not. X is ORed with the quantity y not and z. We could represent it graphically. So this is algebraically, graphically it would look something like this. X, Y, Z. Again, this tells you exactly the same piece of information. You're going to take Y and invert it. You're going to AND that quantity with Z. You're going to OR that quantity with X. So that should tell you that there is an order of operations here. And it just so happens to be very similar to the order of operations of regular algebra. Multiplication before addition, which in this case is AND before OR. And not before all others. So the full rules here. 1, parentheses, because we use those. 2 is not. 3 is AND. 4 is OR. And all of these left to right as you see them. I've seen on YouTube a fair number of videos now saying only 10% of the population can solve this basic arithmetic problem. It's because they write it down sort of douchey. They don't put parentheses in. They don't say what they mean. Don't be those guys. Use parentheses where appropriate. Okay? Don't try to trick somebody up. That's not the point of the course. Okay. And the last way, besides algebraically, graphically, is with a truth table. I'm just going to take this guy and move him, I don't know, up here somewhere. Because a truth table does take up a little bit of space because I have 3 inputs. I have X, Y, and Z, the output F. So I need several rows. How many rows do I need for 3 inputs? I'm going to let you in on a secret. All powers of 2 are even. However, 7 is the last binary combination. It's 0 to 7. I don't know who said that. 0 to 7. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Again, neatness counts here. Give yourself a few spaces so that you can kind of keep yourself neat. I'm not going to outline every row here, but every 2 rows, maybe every 4 rows, just to keep myself neat. So, without going into too much detail on why this is the case, the truth table for this is 0, 1, 0, 0, 1, 1, 1, 1. And you can follow through any line of this and see that it does, in fact, turn out correct. Somebody pick a number between 1 and 7 inclusive. 0 and 7 inclusive. 6. 6 is a 1, 1, 0. So what we're going to do is we're going to trace this value all the way through. So when I take 1 and I send it through an inverter, what do I get? That's what I have to ask myself. I can go back and look at the truth table. Not, however, is pretty simple. You put in a 1 and you get out a 0. Then I have to ask myself, okay, this AND gate, what is 0 ANDed with 0? It is 0. AND is only true if both inputs are 1. So there we go, 0. Now I have a 0 here, and this 1, which has kind of been sitting here, 1. What is 1 ORed with 0? 1. So in fact, none of this mattered. Right? We could have just looked at this as a 1 and said, okay, so let's find row 6. Here it is. It's a 1. Done. All right. This process is how you would derive your truth table from your logic diagram. All right. So we're going to start the next thing. There are some rules. In addition to parens, not, and or. That's your order of operations. There are a lot of rules in Boolean algebra that make equations simpler to handle. A few of them are just going to be kind of duh, and we'll get into the more interesting ones. So when I take a Boolean variable, this is something that could be 0 or it could be 1, and I OR it with 0. This is a law that says you will always get whatever you put in. The reason is if I go and look at x and y and OR 0, 0, 0, 1, 1, 0, 1, 1, what is the truth table for this? 0, 1, 1, 1. So if x is 0, or actually let's swap those around just to make it a little simpler. X, y. So here's x in this column. If I'm ORing it with 0, y is 0, what do I get out for putting in a 0 and putting in a 1? I get exactly the same thing. So when you take a 0 and you OR it with something, you get that something out. When you OR something with a 1, what happens? So again, x ORed with 1. If you put in a 0, what do you get out? A 1. When you put in a 1, what do you get out? So one might say it doesn't matter what you put in. You always get out a 1. There are similar rules. By the way, this is called the identity and the null. There are similar rules for ANDing. If I take x ANDed with 0 or x ANDed with 1, let's look at that. AND. Again, the truth table for AND 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1. So if I AND something with 0, I put in a 0, I get out a 0. I put in a 1, I get out a 0. So does it really matter what I put in for x? No, I always get a 0. And if I AND something with 1, I put in a 0, I get out a 0. I put in a 1, I get out a 1. So whatever I put in, I get out. These are the first of several rules. I know I'm treading short on time here. There are some other rules that start to let you reduce multiple variables. Before we get to multiple variables, what happens if we have 2 copies of the same variable? X ORed with x. Well, to figure that out, or x ORed with x, I just look at rows where they're the same. Right? The middle 2 rows, they're different, so it doesn't apply. But when they're both 0, I get a 0. When they're both 1, I get a 1. So as a result, x ORed with x is x. X ANDed with x is also x. Now we start to add in larger equations. Let's start with the simplest extra function. X ORed with x not. So remember, this is either going to be 0 or 1. And if it's 0, this term will be 1. If it's 1, that'll be 0. So what's 0 ORed with 1? 1. What's 1 ORed with 0? 1. Okay? And the corollary here, x ANDed with x bar. Again, what's 0 ANDed with 1?
0.
What's 1 ANDed with 0? 0. Okay. There is one that doesn't have a corollary when dealing with and, or sorry, dealing with not. If we invert something twice, we end up back where we started. So x knotted and then knotted again is just x. So it doesn't have a split personality there. So those are some identities that we use. Then there are a few things that should come as no surprise to you. Things like commutativity, associativity. X or y is the same as y or x. The order doesn't matter. X ANDed with y is the same as y ANDed with x. We can also associate x or y or z with parentheses here is the same as x or y or z. Ooh, my face is just a little bit in the way. Or z with parentheses there. And the same applies with and. X and y and z is equal to x and y and z, regardless of where your parentheses are. I want to leave you with this last rule because it's the one that is the most interesting. Here I've got a mix of and and ors. It's the first time we've done this. In algebra, what could you do to this equation to change it, simplify it? You can distribute. So that becomes x anded with y, or with x anded with z. Fine, dandy. Okay, here's where things get interesting. You can also distribute across an or. This becomes x or y anded with x or z. So you can distribute across an or the same way you can distribute across an and, which is something to keep in mind. So we'll use these additionally as we go on. Lab today, bring your lab kit. If you have not gotten your lab kit, we're going to have to work it out. But you will be working today in lab. Please at least try to have a breadboard. And a pair of wire strippers. What?